Good morning student, myself Dr. Sanchita Awasthi, Faculty of Oriental Institute of Science and Technology, and today we'll discuss about numerical differentiation. So with the help of numerical differentiation we can calculate the derivative or derivatives of function with the help of some tabular values of independent and dependent variables. So these are the uses of numerical differentiation, or I can say these are some advantages of numerical differentiation over analytical method. So first one is that if we know the tabular values of some arguments or entries, then with the help of that data we can easily calculate the derivative of function without exactly knowing the equation of that function. For example, if we know the values of fxi's at particular xi's, say for some I equals to 1, 2, 3 and n, then with the help of this data we can calculate f dash x at any particular point of x, provided that x should lie between these two extreme values of xi's. That means that it must lie between 1 and n. Second advantage of this numerical differentiation is that with the help of this method we can easily calculate the derivative of those functions whose calculations from analytical method sometimes become difficult or complicated. Now this is the working rule of numerical differentiation. With the help of the data of xi's and fxi's, suppose if you have to calculate the derivative of a function, or we can say first derivative of function, then we can calculate it as a method of interpolation. So choice of interpolation to be used is depend upon the assigned value of x at which dy by dx is desired. If the points are equally spaced, and suppose we have to calculate the first derivative near the beginning of the table, then we have to use Newton's Gregory forward interpolation formula. And suppose if we have to calculate the derivative at the end of the table or near at the end of the table, then we have to use Newton's backward interpolation formula. Suppose if we have to calculate the derivative at beginning of the table, then we have to use Newton's forward interpolation formula. And we know that Newton's forward interpolation formula is given by this series: y at particular point of x is equals to y naught plus p del of y naught plus pp minus 1 upon factorial 2 del square y naught, and so on. In this series, y naught represent the value of function, the first value of function. Del y naught, del square y naught, del cube y naught, all this represent the represent the forward difference operators, first forward difference operator, second forward difference operator, and so on of the first value of the function. Here the parameter p is defined by this fraction x minus x naught by h. Here small x is the point at which we have to calculate the derivative, x naught is the first value of argument, and h is the value at which h is the interval of differencing. In this method our values of arguments are equispaced. That means the difference between any two consecutive value of x is same, and that difference I have denoted by this constant h. So as I have written in this series, you can see the equation number 1. Y at particular point of x is given by this series. At the place of x we can write it as x naught plus ph by this fraction. Here from this fraction we can easily calculate x equivalent to x naught plus ph. So we can write x naught plus ph in place of this x. So this series becomes, so the equation 1 reduces to this form. Now we want to calculate the first, suppose we have to calculate the first derivative of function, then we have to differentiate this series with respect to p on both sides of the equation. Now if we differentiate this factor, and then first of all we have to differentiate this function. So differentiation of this gives y dash x naught plus ph, and when we differentiate this x naught plus ph in terms of p, with respect to p we get here h. And similarly we have to do the differentiation on this side also with respect to p. So after differentiating we get this as y dash x naught plus ph. I have transferred this h to this side, so it becomes 1 by h here, and differentiation of the series left hand side with respect to p gives us this much. So with the help of this series we can easily calculate the derivative of y, the first derivative of y. del y naught, del square y naught, del cube y naught, all this we can obtain by forward difference table, by constructing forward difference table, which I have told you in my earlier videos. H is the interval of differencing, P is the parameter which we can calculate by this formula, x minus x naught by h. Putting all these values here, we can easily calculate the first derivative of function at particular point of x. Now if you want to calculate the second derivative, we have to again differentiate this equation with respect to p, and putting all the values, we can easily calculate the second derivative also. In the similar manner, we can calculate all other higher order derivatives. So this is all about numerical differentiation, and in my upcoming videos I will tell you how to solve problem based on this method. Thank you.